Okay, hello class. Today we are going to predict whether a precipitate will form when two solutions are mixed, given the appropriate KSP values. This is the second play posit of 3 for solubility equilibrium. It pairs well with the equilibrium FRQ problems. When we use the word predict, we are definitely talking about the reaction quotient. We're going to have to compare Q and K, although it's a little bit different when we're looking at solubility product constants. So, will a precipitate form? When we're looking at the comparison of Q versus K for solubility, it's a little bit different than just shifting left, shifting right, or at equilibrium. We can actually attribute some meaning to it. So, we have 3 states that we've talked about at some point or another. We have the supersaturated state, that is when Q is greater than K. This most definitely is when we get precipitate formation. Just to remind yourself, precipitate can be abbreviated as PPT. It doesn't stand for PowerPoint, it stands for precipitate. Okay. When they are equal, we have a saturated solution. There's a really good POGL I know a lot of people did in honors dealing with saturated solutions. The saturation point is when you are at the max. We can't dissolve any more solute past that point. So it makes sense that when we are greater than that, we are supersaturated and we have precipitate forming. All right, and then we have Q less than KSP is unsaturated. Okay. A nifty little trick I learned recently that actually helps me determine the shift. If we look at our Q versus our KP, so in this one it is greater, we know precipitate will form, so it will shift that way, that we can actually make an arrow out of it to make more precipitate. If we are unsaturated, so QSP, KP, KSP, sorry, my bad, that's a typo. If we are unsaturated, we'll shift the other direction, okay? So keep that in mind. All right, so our first problem, and this is one of the ones from the Namesy packet. A solution is prepared by adding 750 milliliters of 4.0 times 10 to the negative third molar, I believe that's cerium nitrate, to 300 milliliters of 2.0 times 10 to the negative second potassium iodate. So will cerium nitrate precipitate from this solution, given this KSP value? Okay. So again, we really only care about the things in the net ionic equation. Okay. So I know that here's my cerium iodate. This is my solid. And the equilibrium I'm looking at is here, okay? So, to figure out QSP versus KSP, well, I'm already given KSP. I need to figure out QSP. Now, the tricky part here is that they give us a variety of concentrations and different volumes, so there is a little bit of a dilution going on. When we mix these two together, it will change our concentration, both because the reaction's happening and also because our volume is changing. So let me make a little note here. Our new volume, 750 ml. 750 ml plus 300 ml. It's going to give me 1,050 ml. Okay. And when I do my calculations, you can either convert your milliliters to liters if that's easier for you. If you want to work in millimoles, you can. It will still cancel out the same way. But bottom line is I need to figure out what my new concentrations are. Before I do that, I just want to remind myself of what the change is here. So x and 3x, because that will potentially impact some things later. It's just good to keep in mind. All right. So before I plug in anything, let's figure out my new concentrations. So concentration for my cerium. All right. My cerium nitrate concentration is going to be the same as my cerium 3+ concentration. So I've got 750 ml times 4.0 times 10 to the negative third molar. All right. So if we think in terms of moles per liter, the liter cancels and we're left in milli. And I'm going to divide that by my new total volume, which is going to be 1050 milliliters. The milli cancels, and I'm back in my molarity. Okay, so I'm going to go through and calculate that. 750 times 4 e to the negative third, and I want to divide by 1050, and I get my new concentration of 2.86 times 10 to the negative third molar for my Ce3+. Okay, and I'm going to go through and do the exact same thing for my iodate. So I've got 300 milliliters times 2.0 times 10 to the negative second my iodate, and my new volume is 1050 milliliters. Okay. To the negative second divided by 1050, and I get 5.71 times 10 to the negative third. Okay, 5.71 times 10 to the negative third molar, and this is for iodate. Okay, iodate minus. All right, so I'm actually going to take these numbers. I'm going to clear some space for myself here. I'm going to take these numbers and plug them into my QSP expression. Now, the QSP expression is the exact same thing as the KP expression. It's just when we're not at equilibrium. So let's take a look. We've got QSP. You would set it up the same way as KSP. We've got my cerium concentration, and you've got your iodate concentration cubed, okay, based on the balance equation. So let's plug it in. I've got 2.86 times 10 to the negative third for cerium, and then I've got 5.71 times 10 to the negative third cubed, and let's see what this gives me. So I've got this. Actually, I'm just going to go cubed. So I'm going to cube that first, and multiply it by 2.86 e to the negative 3. And I get 5.34 times 10 to the negative 10th. This is my QSP. All right, so you always want to compare your QSP to your KP. So if we look, 5.34 times 10 to the negative 10th. This is my QSP, and my KP is 1.9 times 10 to the negative 10th. All right, well, it's nice. They're both in tenths, so you can see this one is larger. So if we go back and review, sure enough, when we are larger, we are supersaturated. Yes, the precipitate forms. Okay. And if you think about it, we're going to shift back to make my solid. So we're going to shift away from whatever reactant concentrations we have, and we'll make my solid that way. So again, we had some concentrations here and here, and we're going to shift back this way to make my precipitate. So keep in mind that what I wrote up here is the dissolving process. If you flipped it, it's the precipitation process. We are shifting towards the precipitation process. Okay? So go ahead and do one on your own. Okay. So we had to set it up the same way. First things first, we want to look at whether or not barium phosphate forms. So if barium phosphate's forming, that means sodium is a spectator. The other thing that's a spectator is my chlorine. And if I look, here we go. I even showed that in here too. My original balance equation, sodium phosphate plus barium chloride gives me barium phosphate and sodium chloride. I really only care about the barium ions and the phosphate ions, so I showed you my net breaking down there. Okay? So same thing as before, 50 times 0.0025 molar, which is my barium concentration, then divided by 100 milliliters. I divided by 100 because we've got two volumes here. We've got 50 and 50, so keep in mind that you're using the total volume before you figure out KSP. That's a common error, common mistake, right? Because we're diluting things when we mix them together. We now have a new volume, okay? That also means we have more solvent, so that can affect things. So then I plugged it in, I got 1.25 times 10 to the negative third cubed and 1.25 times 10 to the negative fourth squared. I end up getting 3.05 times 10 to the negative 17th for my QSP. And that is certainly several factors larger than KSP, which is very, 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 very small. So we shift to form precipitate. Okay. So one of the other things we're going to really need to focus on is what's called qualitative analysis. So this is a lab-related question that AP loves to ask. They can give you some sort of mixture, and you have to figure out how to separate the ions or the solutes in that mixture based on solubility rules. So there's a couple things we need to know. We need to know the common ion effect that we talked about in the last play posit. We need to know the effect of pH, the effect of different solvents. So essentially what a qualitative analysis scheme allows you to do is to separate all of your ions. So in this particular chart, they know that based on the solubility rules, there are all of these ions in a solution, and they have a few of them that will not stay soluble in the presence of chlorine. So you've got silver, mercury, and lead. Those are the three insoluble chlorides. So one thing we could do in lab, we could add 6 molar hydrochloric acid. We add that 6 molar hydrochloric acid, then we can knock out our first row there, and we get all of those things back in as a solid. Now, the other thing that's really cool is that if we use temperature to our advantage, we can redissolve some of those solids in a separate container and filter them out. So that's something we'll have to keep track of there. In this particular one, after they add HCl, they add some hydrogen sulfide and then a dash of HCl, and then this allows you to pull out all of the sulfides. You see that you have a whole row of things that are insoluble in the presence of acid sulfides, and then we just keep going and going and going until we eventually filter everything out. Now, you'll have to use other techniques to filter out within a section, but this is something that is very common. So start reviewing your solubility rules. We will likely have a few of these in our solubility packet that we can look through. And then we can always back these types of problems up, the selective precipitation with numbers. There are some problems with selective precipitation that we have to calculate as well. Okay, so you can do qualitative and quantitative with that. All right, so let's do one. So a solution contains 1.0 times 10 to the negative fourth copper plus and 2.0 times 10 to the negative third lead 2 plus. They said if a source of I minus is added gradually to the solution, which one will precipitate first? And they want to figure out the concentration necessary to begin the precipitation of each salt. So essentially, if we go back, in this one, I guess we're looking kind of in this region. They say we've got copper and lead. So just like they added HCl in this particular picture with the idea that Cl minus would help pull those things out of solution, in this problem we're adding I minus instead, and that will help us pull these two out of solution. So we want to figure out which one will happen first. Okay. So how do we go about that? Well, essentially it's two KSP problems in one. We do have to compare both of them, especially because there is a common ion. Okay. So the nice thing is we have our initial concentrations of our copper and our lead. We have our KSP values, and we just need to solve for the amount of iodine that we need. So let's set it up. We've got our lead iodide as a solid, and we got lead 2 plus and 2I minus. All right, and we know that our KSP expression will lead to I minus squared, and that's equal to 1.4 times 10 to the negative 8th. Okay, and then we're also going to do a separate one in a few minutes with the copper iodide. So let's plug them in. We know that we know what our lead concentration is already, which is nice, and we just need to solve for the I minus concentration. So if we were to rearrange, we know that I would be equal to my KSP over my lead concentration, so lead 2 plus, and I would have to take the square root of that because I squared is involved here. So I can plug in 1.4 times 10 to the negative 8th, oops, and that is over my lead concentration, 2.0 times 10 to the negative third, square root that, let's plug it in and see what we get. Okay, so 1.4 e to the negative 8th divided by 2.0 e to the negative third, and I get 7 e to the negative 6, and I want to square root that. Okay, so I get an I minus concentration of 2.65 times 10 to the negative third. All right, 10 to the negative third molar I minus. All right, so that's one. Now I need to get my second one. We're comparing the two. So this time I've got CuI. Now it's Cu plus, I is a 1 minus charge, so it's just CuI. This one we get Cu plus and I minus, which means my KSP is the same thing, Cu plus, I minus, and there are no exponents here, and my KSP value is 5.8 5.3 times 10 to the negative 12th. Okay, running out of space there, but that's all right. So I need to plug in my copper value, but let me rearrange first. So I minus is going to be equal to, this time, just KSP divided by my copper concentration. No square root needed. All right, so KSP 5.3 times 10 to the negative 12th. And my concentration of copper is 1.0 times 10 to the negative 4th. So 5.3 divided by 1 is still 5.3. 10 to the negative 12th divided by 10 to the negative 4th can be 10 to the negative 8th. You can check me on that. So E negative 12th divided by 1 e to the negative 4. 5.3, 10 to the negative 8th. All right, molar. And this is my I minus concentration. Okay, so then let's go back and identify what the question is originally asking, which is going to precipitate first. Well, we need to look at these numbers and figure out what they mean. We are gradually adding I minus to solution. So to figure out which will precipitate first, we have to look at these values. And the one that will precipitate first will have the smaller I minus concentration. Think about that conceptually for a minute. We need a smaller I minus concentration to cause us to precipitate. Once we pass that concentration, we have an excess. And we have an excess, we are supersaturated, and we continue to make more precipitate. So we look at the smaller one. Here is our smaller concentration. CuI will precipitate first. It needs a smaller amount of I to push it in the opposite direction. If we think about equilibrium, we only need 5.3 times 10 to the negative 8 molar to start making precipitate, whereas we need way more than that, 2.65 times 10 to the negative 3rd, to start making lead iodide. So if we're using the one with the smaller concentration, it allows us to shift, especially if we're doing this stepwise. Gradually means stepwise, so we're adding a couple of drops at a time. So very, very small concentration, and CuI will precipitate almost immediately by comparison, okay? All right, time for you to do an example on your own. Sodium chloride is added to a 50 milliliter beaker that contains a mixture of 0.00015 lead 2 nitrate and 0.00035 silver nitrate. We want to know what precipitate will form first, lead chloride or silver chloride. So very similar process. Just have to find KSP, what you really need to find is the chlorine concentration for each. So find the chlorine concentration for each and compare. Okay, so here we go. Found the concentration for each. The concentration for lead chloride is huge. That's going to stay soluble for a long time. As lead nitrate, you need quite a bit of that to get to shift to the opposite direction. But the silver chloride, on the other hand, does not need that much at all. A very little amount. So silver chloride will precipitate first. Okay. And that is all for today.